A very good day to Dr. Yusiza and everyone. My name is Yeoh and I'm from Group 3. Together with my teammates Meng and Ling Ting. Today we are going to present the ATCS project that we are doing for the Digital Automaton and TM Simulation Lab. First and foremost, we'll get into the simulation overview and the problem definition for our project. So the problem chosen for this project is a finite automaton of a lift logic. The objective of this project is to design a suitable state machine with the right control logic to build a reliable lift system. So before we get into the state machine that we are going to use, we will get into the mathematical language of the lift logic. So the mathematical language of a finite automaton for a lift logic can be defined as LM equals to string that brings M to an exact state, where M is the language of LM that contains all input strings by M. After knowing the language of a lift system, we will need to know the lift system's requirements before designing our control logic for our lift system. So in this project, we will be designing a lift system for a 5-story building which allows sequential button presses from inside the cabin and also from the external floor panels. So for each button presses, it will allow the lift to be transitioned to the 3 states from the current states. So these 3 states including going up, going down, or remain idle, which means the lift will be remain at the current floor when the button is pressed, is same as the floor the lift is at. Next, we will be looking into the control logic that we are going to use for our lift system. So when designing the control logic, we will compare 2 fundamental models, which is the deterministic finite automata, also known as DFA, and the non-deterministic finite automata, also known as NFA. So for our system, we will use DFA as our control logic. The reason for choosing this DFA is due to its characteristic, which is predictability. So in DFA, for any given state and given input, there is only exactly one unique next state, and there is no ambiguity. So this ensures the lift will be transitioned to a certain state and also at the same time ensure the passenger's safety because of this certainty. On the other hand, the NFA allows a single input to be split the machine into multiple potential states simultaneously, which is not desired and highly dangerous when we're dealing with the passenger's safety of using this as the lift logic. So by utilizing a DFA, we can guarantee a single, determined, and mathematically safe path for every single passenger's request when using the lift.
Hi, I'm Meng. So I will be talking about the 5 tuple definitions and also the transition functions for the 5-floor elevator DFS system. So the DFS for the elevator is defined by the 5 tuple M is equal to Q, sigma, delta, Q0, and F. So the symbol of Q representing the set of states. For our system, all the set of states are S1, S2, S3, S4, and S5. So each of these states Sn representing the lift being stationary at floor N. Then we have the symbol sigma, which represent the input alphabets. So in our case, we have B1, B2, B3, B4, and B5. Each of these symbol Bn representing the user pressing the button for floor N. Then we have the symbol of Q0 representing the initial state. The initial state of our system is S1. The lift is assumed to start on ground for S1 upon machine initialization. Then the symbol F is the set of final state. So we have S1, S2, S3, S4, and S5 for our final states. In control systems like the elevator, every floor is a valid halting or accepting state where the doors can open and complete this process. Then the transition function delta is just like the rules that telling how the lift move between the floor based on the input. Now let's talk about the transition functions of our 5-floor elevator DFS system. So N is representing the number of floor and M representing the number of the buttons that the user presses. So for all 5 greater than or equal to N and M, and also N and M must be greater than 0, then we will have a formal rules notations for our elevator, which is delta bracket Sn, Bm brackets equal to Sn. So these formal notations tell us that if we are at the floor of N, if we click buttons M, then it will bring us to the floor M. So below shows the transitions table of our DFS system. So it's give a very brief and overviews of our transitions function. So for example, at floor 1, S1, if we click on the buttons V1, we will be remained at the floor 1, S1. So if let's say we are at floor 2, S2, if we click on the button 5, we will be moving up to floor 5, S5. Similarly, if we are at floor 5, S5, if we click on the buttons of 3, we will be going down to floor 3, S3. So this page show about the descriptions of the transitions functions of our system. So for our 5-floor elevator DFS system, the transitions function can be divided into 3 actions. The first one is the stationary transition, self loop. Then the second one is the upward transitions, where it brings us to go to the higher floor. Then we have the downward transitions where it brings us to the lower floor. So for the transitions functions, it's function as if we are at S1, if we press B1, then we will be remain at the S1. Similarly, if we are at S3, if we click on the buttons of B3, then we will be remain at the floor 3, S3. For upward transitions, meaning that if we are at the floor like S1, then if you click on the buttons B2, it will bring us to the floor 2, to a higher floor, floor 2. Then if we click on the buttons of B3, it will bring us to the highest floor, floor 3. And similarly, if you click on the B4, then it will bring us to the higher floor, S4. If we are at from S2, if you click on the buttons of B3, it will bring us to the higher floor, S3. Then if we are at the S2, then we click on the buttons of B4, it will bring us to the higher floor, S4. So for the downward transitions, if we are at the floor of S5, if you click on the B4, then it will bring us to down to floor S4. Then if we are at the S4, at the floor 4, then if you click on the button 2, B2, then it will bring us go down to S2 for 2. Yeah, that's all from the transition function. Thank you.
Okay, to design and test our DFA for 5-floor lift, so we are going to build the state diagram based on what is mentioned by our members earlier. So we'll have 5 states here modeled inside our automation simulator. For these states, each of the states have 2 types of movement operation or the state transition. So the first one is the self loops. So this is to simulate when the state is on the certain floor and when the user is input on the same floor. So as you can see, if it is on M and the user is pressing the button for the same state, it will move back to its on state. So for example, it's on floor 1, then when the user is pressing the first floor button, it will go back to state 1. So the other types of transition is the up or the down. So this is to simulate when the user is pressing the button to other floors, which is maybe from the floor 1 they press to floor 2 or floor 3 buttons, then it will move to their respective floors. In this state diagram as well, you can see there's a start here because the automation studio will require the users to start the state on the start state and doesn't allow for the renaming of the state. So we're going to use the start as the S1. So both of them are having the same types of the transition, which is when it's moving 1, it will go to the state 1. So to other steps, it will move to other states as well. So we can treat the start as the S1, which happens to be the start state as well. So we choose DFA for this application is because all of these states is already finite states. So all the transitions can be defined properly. So there's no loops required as well. So we don't need to match a certain number of inputs. So therefore, we don't need any stack like in the push-down automata or the tap in the Turing machine case. To test the DFA systems, we're actually using the simulator inside the automation simulator. So over here, you can see there's a test and debug button where we click on where it enters a certain input. Then we can step it from one step to another step using the transition, and we can see the test result for all the inputs. So when the automation is finished, it will end in one of the state that is accepted, which you can see the blue tick at the left side of the states. Then it will be accepted. So when the automation should be rejected, then it will go to a rejected state. To set up our test, we will be first using the string 132. So you can see it start with the state 1 and proceed to the state 3 and to the state 2, which is an accepting state or the final state. So the expected result is this string should be accepted, and we have the result that this string is accepted. Similarly, we carry out another test, which is the string 51. Then we'll proceed to move to the 5th floor and to the 1st floor. Then the expected result is the same. It should be accepted, and the actual result here shows it is accepted. On the third test, we are going to test with a unknown input, which is 6. So we'll be carrying out with the 1, 6. Then you can see the result is a rejected because the 6 transition is not over here. So there's no 6th floor involved. So you can see the expected result is a rejected, and the actual result is also rejected. Similar as before, we're going to test with another unknown symbol, which is 7, another input string. Then we will see it will fail right off the start. So the expected result is also rejected, and the result is rejected.
A very good day to Dr. Yusiza. I am Yeoh and I will be kickstarting the self-reflection section for myself and my team. So start from me. I, as a leader, will be responsible for distributing the parts of the project to each of my team members and ensure they do their parts accordingly. So for my part, I'll be creating the list of the subpages of the wiki and also the simulation overview of and the problem definition of this project. So in this project, I decide the title to be chosen is the using finite automata for the lift logic system. So in this project, I learned how to differentiate DFA and NFA, and also how DFA works and NFA works, and why they are different, and why DFA is more suitable than NFA for lift logic. I also like to take this opportunity to express my gratitude to my team members Lee Meng and Ling for their cooperation in completing this project smoothly.
I'm coming. So I'm doing the Phi tuple definitions and also the transitions functions part of the project of the Phi floor elevator DFS system. For my task, I learned how to turn the real world into a formal mathematical models. Working on the Phi tuples taught me how to clearly define the states, inputs, and start and accepting state of the elevator. Creating and the transition function showed me how to map out every single movement of the elevator from floor to floor. This taught me how to think logically and make sure the system never gets stuck or confused by any sudden user inputs. I really want to say a big thank you to my teammate Khai and Ting for all your supports. We did an amazing job communicating with each other from start to finish. Even though we separated our tasks, our teamwork made everything fit together perfectly. I really appreciate how we share our ideas and help each other in this project. Thank you.
Working on this project really helped me understand how a DFA works just beyond theory. At first, the idea of states and transition felt very abstract, but modeling something familiar, such as the elevator, actually makes me understand more. So I can actually see how each floor is a state and how each button press is an input symbol really helps to visualize this whole DFA concept. The biggest challenge is to realize the machine needed for a complete set of transition, which is a 25 transitions, and then how each floor can reach to every other floor, and to map all this actually taught me to be more careful and systematic, as well as to study more in detail on how the states can transition to each other and how this lift actually can be operated in real life. So I also learned why DFA was the right choice, because there's no counting, there's no loop involved, so we don't need any stacks like the PDA or a tab like the Turing machine. So if I did this again, I can determine which kind of the state machine or which kind of the automation will be required for each type of the applications. And nonetheless, I want to thank my teammates as well, Khai and Meng, for their help and support throughout this project. Without them, this project couldn't be run so smoothly. So really thank my teammates for this whole projects and how we can work together despite not meeting each other in real life. So really thank you. And also just overall, this project is really very interesting and helpful in our understanding for the concept of the theory of computer science. Thank you.